cos of pi, that's minus 1. Minus 1, not 1. It's minus 1. And of course the sine theta over 2 for theta is 2 pi, that would be sine 2 pi over 2, which is just sine of pi, which is nothing. So that's the same, the 0 is the same. But this here is now minus. So in other words, for theta is 360 degrees, this is minus of the original. Minus. Okay? Now for some things, that difference doesn't matter. Like for example, in this case here, if you're calculating the expectation value of z dash, where z dash now is like 360 rotate, theta is 360, you'll get, because of the square here, doesn't matter. It'll come out the same. But if you're doing like interference type experiments, then it does matter. That difference, where the dashed forms are the negative of the theta 0, then it does matter. So interference type experiments, it is of importance. So quantum mechanics, quantum mechanical spin is really weird. Weird. As I keep saying from the very first lecture in quantum mechanics, you expect that. So in other words, what do you have to do in terms of rotations? What does your theta have to be so that things are restored back to as if theta was 0? Well, the answer is you have to rotate it through twice, right? 4 pi, 2 full rotations to get back to what you had. And that, if you think about it, that comes from the result in the spin matrix mathematics of the pi over 2, sorry, the theta over 2 factor. That's where this weird phenomenon comes from. So here is a kind of warning. Now I've been saying all along, you can think of spin, quantum mechanical spin, as a kind of spin about its own axis, like the Earth spinning on its own axis. So there's two kinds of spin in a sense for the Earth. There's the orbital angular momentum as it spins around as it orbits around the Sun, and then there's the intrinsic spin as it orbits, well, as it rotates about its own axis. Okay? Now that analogy is not strict. It's a rather crude analogy, because there's nothing in the classical world equivalent to this. You have to rotate it by 2 rotations to get back to the equivalent of theta is 0. There's nothing like that in classical mechanics. So it's it's specifically quantum mechanical and very weird. So this analogy, and it's only a rough one, between the spinning Earth, spinning planet, and the spinning particle, is crude. It's a crude analogy. It's not close. So in other words, don't be too literal. Okay. So this the electron spin. There's nothing equivalent to that in our human scale, macroscopic world. So be cautious of that. All right, new topic. Just starting. Okay, we've been talking about spin, and before we were talking about spin, we were talking about wave functions with spatial properties. R, the position vector. So now that we've done spin, so in a sense we're sort of more or less finished with the mathematics of spin. Now we can get back to sort of standard quantum mechanics, wave functions and Schrödinger equations and all that stuff. But now that we know about spin, we can incorporate in the wave function not just spatial factors like R. The wave function size is a function of not just R, the position, but also spin. So you can put an S in there. Now, to deal with that kind of quantum mechanics thoroughly in detail, you need the full-blown theory of Dirac's relativistic quantum theory. Now, relativistic means you have to bring in Einstein's special theory of relativity, and that's definitely not undergrad level course. So we will deal at length, several courses on Dirac's relativistic quantum theory, the famous Dirac equation. So, but we can still do some. Without using Dirac's full-blown theory, we can still do some quantum mechanics using where the wave function is a function not just of position r, but also of spin. But that will be for the next session. Give you just sort of a lead in here. I'm curious to see how this looks, because the camera is much closer than when I was using it before. When I was using the living room with the old board, well, the number 2 board. This is the number 3 board. So I'm curious to see how this works. It may not be successful, but we'll see. Ciao.